Hey, this is Jesse with Create This. In this video, I am going to put together an Anderson connector for my Yeti 400 that will be battery protected, so voltage protected, and it will allow me to run my 12 volt fridge, my Engel 12 volt fridge, off of my Yeti 400 battery without resetting the circuit breaker on the 12 volt DC plug port. So I did a previous video where I showed that 12 volt circuit breaker resetting, and then I had talked to the Yeti 400 support team, and they told me that the reason why that's happening is because the Engel fridge compressor, when it starts up, it has an inrush current that exceeds the current limit on the breaker for the Yeti 400. So the way to get around that is you use the Anderson ports on the side, and one of my viewers actually commented on that video and said, yeah, you can use the Anderson ports on the side. But the problem with doing that is you risk destroying your battery because at that point it's not voltage protected, so you're not going through the battery management system on the Yeti 400, and you can drain your battery and destroy it, right? So that's what this thing's for. This is the APO3. It's a battery management system, and it has set points selectable via a dip switch that allow you to choose which voltage you want to turn off the circuit at. So there's like a relay in here, and it'll shut off if your battery is below a certain voltage set point. And I'll show more about how to configure the dip switches on the APO3 in a minute. And I'll also show all of this wired up. But these are the parts that I ordered for this project. So I've got an external 12 volt receptacle, and it came with these clamps here, and I got all this stuff on Amazon. It came with these clamps. I'm going to cut these clamps off, and I'm going to replace them with Anderson connectors. So I couldn't find like a 12 volt receptacle that already had Anderson connectors available. And the other reason why I went with this particular model is because it's got individual cables, and I've got a current meter for my oscilloscope, and so I'm hoping that I can check the inrush current and actually see what that looks like on the oscilloscope and show that to you. But anyway, so we're gonna chop these off, and we're gonna put Anderson connectors on it. So I bought a little package of Anderson connectors, and this is a crimp tool for Anderson connectors, and then this is my battery management system. So all of this stuff I got on Amazon. I like to buy all my stuff on Amazon because it gets shipped to my door, and I don't have to go out and like go searching for it and scratch my head a lot. I'm going to have links to all of this stuff down below in the description. So if you want to, if you like any of these tools and you want to pick them up, or components or whatever, and you want to pick them up yourself, feel free. I do get a small commission when you order them through me, and it just helps me keep the channel going. So it doesn't cost you a dime extra, but it helps me continue to buy cool stuff. So and do cool reviews and all the stuff that I do on this channel. So anyway, let's get on with creating this this wiring setup so that we can run some tests and see how it works. Okay, so the first thing that I need to do is I need to chop off these clamp connectors so that I can put on these Anderson connectors. Now, I've never worked with Anderson connectors before. This is my first experience using Anderson connectors, but I've used a lot of other crimp-on connectors, so hopefully it's not rocket science, right? Let's see, I do have a set of clippers here. I guess I didn't display them in the previous frame where I showed all the tools and parts and stuff. I'll include a link to these as well. I like this particular brand. It works really well. And I also have wire strippers. I'm not even sure if I'm going to need these, but we'll see. So first thing I'm going to do is I'm just going to snip off the wires here. Boom. I hate doing this. It's a perfectly good pair of clamp connectors. Maybe I can reuse them for something else. Okay. And then the next thing I'm going to do is I'm going to strip these down, and let's see here. Doesn't look like particularly high quality wire to me, but it looks like maybe it's a 12 gauge. It's not really a tight strand bundle. I'm not real happy about that. but whatever. So we'll try using it in the 12 gauge side of the stripper here. Now again, I've never used these Anderson connectors before, so I don't really know how much I need. Yeah, all right. You get to watch me make an idiot out of myself. That's the fun thing about YouTube, I guess. Okay, that worked pretty well. That worked pretty well too, cool. And yeah, I guess those guys could just go on there like that. I'm glad it fit. I was a little worried it wouldn't for a second there. So I've got these ratcheting crimp tool things. This is the crimp tool that the people selling the Anderson connectors on Amazon recommends. It's a little more expensive than the one that's a little bit more popular, but I figure if they recommend it, it's probably pretty good. I like to buy quality tools. The poor man pays twice, they say. Usually that's accurate. So the way these work is they ratchet down, and then you squeeze them a little further, and they release. So let's see. I'm really not sure how this works, but I think let's try the 45 first. I think the doohickey just goes in there, and then you just crimp down on it. Let's see if that worked. No, not a very tight fit. Let's try that again. We'll try the 30 this time. So I'm just sliding that into the slot, and then okay. That's a nice fit. That's good. Okay. Now, unfortunately, okay, yeah, I think this was the red. I'm going off of memory here. No, okay, yes, it's definitely the red because it's the one that has the white stripe on it. So that's good. All right, so I assume, you know what they say about assumptions, right? I assume that this guy just goes in there and snap fits. But who knows, man? Who freaking knows? There we go. Nice solid connection. All right. Then we'll do the second one. I think I had that last one pointed down, so I'll try to do the same thing. It's got this little profile on the side. I'll just try to point that down because I think that's what I did with the last one. Trying to get all these wires in there, man. You know? Don't want to waste any. It's good copper. There we go. Got them all. All right. And again, I'm going into the 30 port. There's a little hole down there at the bottom, and I'm just putting the thin part of the adapter into the hole. And then once it's in there, I just clamp down. It requires a little bit of, you know, arm strength, hand strength, whatever. Give it a little tug. Seems like it's in there pretty well. All right, and then it's hard to see in these connectors. You probably can't see in there, but there's a little metal strip. And I think what you do is the metal strip goes on the bottom of this profile. So there's a little arch here. the metal strip goes on the bottom, okay? So I'm just looking in there, I'm going to line it up, and I just do a little wiggle thing. I'm kind of giving it a little bit of pressure as I wiggle it, and it clicks into place. And then, let me see, do these guys slide together? I think they snap together or something. I don't really know. Yeah, they slide lock. Cool. Cool. So if I have that polarity wrong, I don't know if red goes on the right or the left, but if I have that polarity wrong, I can just slide it back out and reattach it on the other side. So that's pretty cool. All right, so now we've got our connector for our 12-volt receptacle. And what we're going to do is we're going to attach this to this. So load. So we're going to attach this like this. Oh. Let's see. There we go. Boom! Just like that. How cool is that? So that's to the load, and then this is going to go to the Anderson port on the Yeti 400 to the battery. And that's pretty much it. And so this will give me wires that I can put my current clamp on and hook this up to the oscilloscope. And I guess we'll show that next. I really want to see that that inrush current spike. I'm not sure that I'm going to be able to capture it, but I'll do my best. It should be interesting. All right, so this is an APO3, and let's see. It comes with this user manual. You can also get this thing as like a PDF, and let me adjust the brightness here. Oh no, that actually works. Okay, so you can see here that I've highlighted the voltage. You get to set the voltage that you want the device to shut off at. And I've highlighted the voltage that I think is going to work well for me, 12.7 volts. I could also choose 12.1 volts. Now, you know, it's kind of a useless comparison without actually being able to know what the voltage means in relation to the state of charge for an AGM deep cycle battery, which I believe is what is inside the Yeti 400. So I downloaded this this chart from, I mean, I just went to the website from, yeah, so it looks like I got this chart from energymatters.com.au, and it's the battery voltage discharge or the state of charge table. So you can see here for an AGM battery, which I believe is what's inside the Yeti 400, you've got 100% state of charge is 12.8 volts. 75% state of charge is 12.60 volts, and then all the way down to 12.0 volts for a 25% state of charge. So the set points on the APO3 don't really correspond to what I need very well. There we go. You can probably read that a little better now. The set points on the APO3 don't really correspond to AGM batteries very well. They've got 12.1 volts and 12.7 volts. So you can see that 12.7 is somewhere between 100% and 75% state of charge, and 12.1 is somewhere between 50% and 25% state of charge. So the deal with like 12 volt AGM battery, AGM deep cycle batteries, is that like the less you discharge them, the longer they last. So you can get more cycles out of a battery if you only discharge it like 25% over the life of the battery versus, you know, discharging it like down to 50%, you shorten the lifespan of the battery, basically. So you can go pretty low and still get like hundreds of cycles out of it. You can go down to like 25% and probably get hundreds of cycles out of it. But if you only go down to like 75% or 80% or something, you can probably get thousands of cycles out of it. Don't quote me on that because I don't know exactly which battery is inside the the Goal Zero Yeti 400, and I haven't seen the spec sheet and I haven't talked to anybody about it. But that's the general way that these things go, right? You get more life out of the battery if you don't discharge it a lot. So these set points don't really correspond to AGM batteries very well, but you know, I figure I'll start conservative, right? I'll start at 12.7 volts, and that's somewhere between 100% and 75%. And if I find that my fridge is turning off a lot at night, I will either add more batteries via the Anderson ports, or I will lower that down to 12.1, you know, depending on what I feel like doing. So anyway, so let me show you how to set the dip switches on this thing. So I kind of had to figure this out. They don't really have it as part of the user manual, which I thought was kind of weird. It's got these two silver screws right here. You don't want to disconnect. You don't want to unscrew those. Okay. These black screws are the ones that you actually want to unscrew to access the dip switches. So I will go ahead and do that. Okay, and then once you've got all four of those screws off, the top plate just lifts off, just like that. Okay, so you can see in here, I'm not sure how legible that is, but you can see in here that there's a chart that lists the voltage set point, and then it's also got the delay. And I've got my delay set to 10 minutes, so once it goes below 12.7 volts, it'll wait 10 minutes, so that takes care of like hysteresis if you know, you've just got like a load spike or something that draws the voltage down. It has to consistently be below 12.7 volts in order for it to shut off. So I've got a 10-minute delay, and that is, it's kind of, there's some wires in the way there, but I don't know if you can read that, but that's on-off for the 10-minute delay there for pins, or for switches 3 and 4. And then for the 12.7 voltage, that's on-off for switches 1 and 2. And then you can see here are the dip switches. So 1's on, 2's off, 3's on, 4's off. And you can just use a screwdriver to, you know, flip those back and forth. I'll demonstrate that right here. That's off for pin 1. That's on again because it's labeled on at the top there. Okay, so that's how you set the limits, and I'll just put that back together and we'll take it out to the Yeti and install it. All right, so here we are up on the back porch, and we've got my Engel fridge here on the left, and it is plugged in via 12 volt to the Yeti 400. And we can see here that this is the AC power adapter for the Engel, and it is indeed disconnected. So it is plugged in solely via 12 volt. This is the 12 volt power supply, or 12 volt connector for the Engel. This is the 12 volt adapter that I rigged up, my Anderson connector, my battery protector, and it goes right into the side port, the side Anderson connector port on the Yeti 400. You can see I'm not using the 12 volt port on the front of the Yeti 400. And the reason why is because it's got a breaker on it. It doesn't work. So I've been running the fridge like this for about a day now, maybe a day and a half, about 24 hours. And it's been working just fine. I haven't had any of the problems with tripping the breaker. The battery hasn't discharged, you know, unreasonably. I mean, it seems to be working really well. So I'm not going to stop there, though. I thought it would be interesting, now that I have an oscilloscope, to see if I could capture on the oscilloscope the inrush current that the Engel fridge generates when it starts up. So, you know, we would actually be seeing the current spike that causes the breaker on the Yeti 400 to fail. So over here, I don't have a pan head, so this is going to be a little jerky. Over here, I've got my oscilloscope, and let me talk about these pieces here. So I've got two probes. I've got in channel 1 here, I've got this current probe. This is a Hall effect sensor probe, And these are about $800. It's a fluke tool. It looks kind of chintzy, looks kind of cheap. It's got a 9-volt battery back there, but these are really high quality probes. Like I said, they cost about $800, and they have a very high sampling frequency. So yeah, so we're going to be able to use this to measure the current. Then over here, I've just got the standard oscilloscope probe, and I'm going to use this to simultaneously measure the voltage on the battery. And so with these two measurements, we should be able to calculate the wattage of the battery under load during the peak power consumption, or the inrush current. So I thought that would be kind of an interesting exercise. Okay, so one of the interesting things that I found with this current sensor, first of all, it's got a battery in it, so you have to turn it on. I'm using the 100 millivolt per amp setting. And the direction, it's got a little direction meter right here. The direction that you attach it to the cable matters. So we're going to attach it in the direction of the current flow, and that way we'll get a positive reading on the oscilloscope. So I'm just going to attach it to the red wire here. I've already zeroed it out. It's got a little dial for zeroing things out. And then with these Anderson connectors, I have rigged up a little isolation block here. This way these two wires won't touch and short out my battery. And I'm going to plug this in here, if I can, being careful not to short anything. Okay, and we'll attach our traditional oscilloscope probes for channel 2 up to the positive and negative on the Yeti. Now, this is an isolated probe. Kind of, I guess it's similar to a differential probe. Since it's a Hall effect, there's no direct electrical contact. So you don't have to really worry about frying anything with one of those. With one of these, you have to worry about frying something if you've got something mains grounded, reference grounded, whatever. So fortunately here, we're working with a 12-volt battery-powered system, and the only thing that's mains grounded is the oscilloscope here. So we should be able to do this just fine. Famous last words if it doesn't work, though, you know. So let's try this. Put this one ground connector on there. All right, and put our positive probe on. Okay, and I'm going to change my camera angle at this point. Okay, so let's see if we can get this set up. So I am not an expert with oscilloscopes. This is probably my third time in my life using an oscilloscope, but I played with this a little bit before the video. So I think what I want is run on. I want it in single mode. Okay, so I probably should have hit single. And so now it is looking for my trigger voltage, and I've already set my trigger voltage. It's at like 316 millivolts on the current sensor, so it's on channel 1. And I've set that so that it's just a little bit above the normal, the normal current cycle that it pulls from the 12 volt. So that should give us the very first pulse, the inrush current. And so now what I'm going to do is I'm going to come over here to the fridge and I'm going to cycle it on so that it turns on the compressor. And we'll see if we capture anything. There we go. Okay, so this is attempt number 2. This time I've turned on channel 2. Got channel 1, which is my current probe, and channel 2, which is my voltage probe. I've got single set, so we're ready to go. So now I'm just going to turn on the compressor. There's our signal. Turn the compressor back off. All right. So I think what's happening here is the blue line here is our voltage, and the yellow line is the current. And that's interesting. I honestly thought that the voltage would drop as we were doing this, but it doesn't seem like it is. So I spent some time playing with the scale for the channel 2 probe, and I got it to the point where I can see a tiny dip right there, and I used the min and the max functions, so it says 14 volts and 12.8 volts for the min. I don't think that's accurate though. I've got a, let's see, well, got a Fluke 87 here, and this is hooked up to the same inputs. And when I do the min-max on this, it says for the max it's 13.7 volts, and for the min it's 12.91 volts. So I trust the multimeter. I don't really trust the oscilloscope for this. I'm not sure, what the problem is there. Maybe I just don't have the right probe, or maybe the oscilloscope isn't the right tool for the job for this. I don't know. But let's see. At least we got a really cool waveform for the current spike, the inrush current spike. And for that, let's see here. Put it on channel 1, and we'll look at the Vmax and the Vmin. Okay, so for the max there, we've got 1.4 volt. Wait, is that right? Yeah, 1.4 volt, and for the min we've got 16 millivolts. See, I don't even know if that scale's correct though. I'm not really sure I can trust that. Yeah, I don't know. Hard to say. I'm not really quite sure how to make the scale match the actual input on this thing. What I can do is I can attach the same current probe to my Fluke 87. Let's go ahead and do that, and we'll see what kind of a max and a min we get there. Okay, so I'm kind of running out of daylight here, but hopefully you can read that. That's 0.022 millivolts, 0.022 volts. Let's turn on the compressor. And we'll turn it off again. Well, I'll just leave it on-ish. So here, the max says 0.486 volts. And the min voltage is 0.022. Min current, sorry, is 0.022 volts. I guess the best way to do this would be with two multimeters. That way I could measure the current and the voltage at the same time. I was hoping I could do that on the oscilloscope, but it seems a little difficult to do. So using a ratio calculator, yeah, there we go. So 0.1 volts per 1 amp is what the tool gives us. So 0.486 volts gives us 4.86 amps. So that's at the max. So 4.86 amps at the max times, and granted we didn't measure this at the same time, but times 12.91 volts gives us 62.74 watts. So this is what I don't understand. Every time I measure this, it seems like I'm only drawing 62 watts. And they say that the Yeti 400's DC, 12 volt DC power plug trips at 120 watts. So if my max inrush current is somewhere in the 62 watt range, I'm not sure why the breaker is tripping. Yeah, anyway. So I found a workaround, but I don't really get why I have to use it. I don't understand that. Anyway, so hopefully Hopefully you're even more confuddled than I am at this point. This is Jesse with Create This. I hope you learned something, or at least found this mildly interesting. And if you like it, press the like button. And thanks for watching, and please subscribe.